So the same results then for the logistic regression model. So the abridged version of the R output is at the top of the slide, and really the interesting bits of this table of T statistics is the second row downwards. So in this case, what you get is that the p-value at the end is less than 0.05, so this is significant, and it's accompanied here with asterisks, so you know it's significant. The first quote here comes from that it has a significant impact on probability of success, and once it's significant, we look at the sign of the variable. Here it's negative, so load increases, the probability of success decreases. So much of this is similar to what you've seen before, but because this is a probability regression model, it's phrased like this. So as load increase, it's now the probability of success. So it is a probability that these regression equations are referencing, not just the y variable itself. And then I've given an example of the hand calculation of the Z or T statistic, which would be similar to something that might set on an exam in years it's an exam. And then the thing I wanted to emphasize here is again you've got this trick with the inequality sign. So the thing is bigger than 2, which means that the is less than 0.5. Again, the inequality sign is put in a different way if you're doing this bit correctly. I just want to emphasize here that when you're interpreting these probability regression models, strictly speaking, it's a probability, it's not just the underlying variable. So I sort of tried to make a little bit of a song and dance about phrasing this interpretation extra precisely. Since the coefficient of load is negative and statistically significant, as load increases, the probability of success decreases. Okay, so precisely because it is a probability regression model, I've tried to emphasize there that it's the probability of success that increases or decreases depending on the sign of the regression coefficients. Okay, much of this is repetition of what you've seen before in a slightly different form because it's a probability regression model. Note here, again, phrase this in English the opposite way to how you worked it out in the previous slide. So, how is it significant, and if it is significant, the effect positive or negative, and here we've written this down in the Queen's English, negative and statistically significant. Okay, so this is probably the best way to communicate this on an exam or for you guys, the actual assessed coursework. Okay, but the way you write this down is actually the opposite way round to how you actually work it out. Same thing then for the probability regression model. So again, an abridged version of the R output is shown at the top of the slide, and the name of the game here really is to look at the second row downwards. And again, what you see is this coefficient of load is again significant precisely because the p-value listed at the end is less than 0.05. Again, this row is accompanied with the asterisks, so you know that the thing is significant. Where the first point comes from, and then significant. So we look at the sign of the estimated coefficient is negative. So in this case, again, precisely because it's a probability regression model, you can state this that as load increases, the probability of success decreases. I want to give an example hand calculation of the T statistics similar to something I might set on an exam type question. Okay, so what you have in this case is that the p value is 2.0, the p value is less than 0.05, and again, my little trick here that I wanted to emphasize, if you're doing this bit correctly, the inequality sign should point a different way. Okay, and the other thing to sort of say here as well is that necessarily the logit and the probit models are similar, so the way you interpret the results are similar to reflect that, and they are just a slightly different version of the regular regression models. So in terms of extra interpretation then, so just trying to sort of emphasize that these are probability regression models, so slightly different to the classical linear regression models. So I've said this in the first bullet point, since the coefficient of load is negative, load increases, the probability of success decreases. So again, emphasize that these are probabilities because these are probability regression models, that you write this down in the Queen's English, around to how you work it out on the previous slide. And then outside of the exam, with a view towards dissertations and real projects, there can be some nuances in terms of the interpretation, and I don't think I've always had the experience to sort of fully appreciate the value of this, even if I've always been a mathematician. So it's two different sources of information, same thing. I usually phrase this as cross-checks, and it's always worth cross-checking numerical information like this with a graph. We'll go through this on the next slide. The thing I wanted to emphasize here, which again I don't think I've always had the experience to fully appreciate, is that since the logistic and probit models are similar probability regression models, they should give you similar numerical answers for your data set. Okay, so they will actually also serve as a cross-check of each other. So trying to plot the data as a sanity check then, and the important point here I think is to get into the habit of cross-checking numerical information from a statistical model with just a simple graph. So what we've done here are calculate the proportion of failures, and what you see is an almost linear increase in the failure rate as the load increases. Okay, and this is a sanity check because it just checks that we've got everything the right way around. So it's natural to expect that as the load increases, the probability of failure will increase, and not only have we got that the right way around, all the models that we fitted here, the linear probability model, the logit model and the probit model, all return this common sense interpretation. Okay, so if we didn't get this being the case from this graph, the indication would be we'd made a mistake somewhere, either with the graph itself or with the actual probability regression models that we fitted. Okay, now since the graph is the right way around and it matches the results of these probability regression models, we can be fairly confident that we haven't made an obvious mistake. So I just wanted to give some extra calculation examples here for the linear probability model. So you're asked to find the value of the load for which there is a 50% failure rate, equivalently 50% success rate. And the thing to watch for here is, because the linear probability model is just a classical linear regression model in sheep's clothing, this probability calculation should be especially simple. And also what you might look for here is that because this probability is smack bang in the middle of the range of the sample, you might expect that this simple model may still give you a reasonable looking result. Okay, if you're asked to calculate a probability using this model either close to 0 or close to 1, then I think this is precisely where the model is going to break down, but you'd hope you might get a more reasonable answer smack bang in the middle of the sample. So the success probability is just equal to the regression equation. So this success probability is 0.5. You just set that equal to the regression equation and rearrange using algebra to find the load, and the value should come out like that. So the things to watch for here would be, firstly, the load is positive. If it's negative, you made a mistake somewhere, and this number should be roughly in the middle of the table that appears in slide 5.1. Okay, and if you look at that slide, the value of 344.5.087 is roughly halfway down the column. I wanted to now give an extra calculation example for the logit model, and I ought to apologise here that I might write down variously log or ln, and whenever I write log, I mean ln on this course. Okay, so I've included ln here. Log, don't get confused, I still mean ln. It would just be the ln button that you need on your calculator. So you get asked the same question then, calculate the load that corresponds to a 50% failure rate, and we set log of the probability equal to the equation. Then you would just rearrange to find the load as before. The 5, then what you have is ln of 0.5 over 0.5, so ln of 1, which would be 0. So 0 equals to the regression equation, change, and you find the value of load similar. And again, I think because this is smack bang in the middle of the sample, you'd expect all three models here to give you roughly similar answers. And again, if you look on the table on slide 5.1, this value of 3448.535 should be roughly halfway up the first column of the load values, indicating that this is approximately halfway up the sample. So same calculation for the probit model, so expect here similar answers to the other two models, and especially similar match to the logit model. Okay, so you ask the same question to find the value of the load for which there's a 50% failure rate, equivalently a 50% success rate, and so the equation is that the z to the minus 1 of the probability is equal to the regression equation. Then what you have in this case is z to the minus 1 of 0.5 is 0. Works very similarly to the previous logit example. So 0 equals to the regression equation, just rearrange to find the value of the load, and you get a similar answer to the logit model. Okay, 3447.513. So again, a very similar answer to the logit model. And again, if you look back at slide 5.1, this value is roughly halfway up the left column of the load values. Okay, so in both cases then, this value of 3447.513 seems similar because it's roughly halfway up the original sample, and it is a very similar answer to the answer you get for the similarly oriented logistic regression. So I want to now give an example calculation with the linear probability model. So you're asked to find the success probability if loads of 1999 kilograms and 4891 kilograms are applied. So the solution to this is just set the probability equal to the regression equation and plug in these numbers of 1999 and 4891. And you see that in this case, these estimated probabilities exceed 1. The load is 1999 if the applied load is 4891. Now the question here is, do you think these are sensible probability estimates? Well, hopefully we can agree from high school maths that all probabilities have to lie between 0 and 1. So what I've managed to do here is find two numbers that break this simple model. Okay, so we saw in the previous numerical example that if you've got a data point smack bang in the middle of the sample, then you might still reasonably get sensible answers from this linear probability model, but we haven't had to work too hard here to find values that have sort of broken this simple model and probability estimates that don't really make sense. Now, of course, you could sort of estimate these as success probability 1 and success probability 0, but nonetheless, I think you can sort of see here that at precisely this range of values, this probability model begins to break down. So, alongside that, then I wanted to do the same calculations here with the logit model. What's the success probability if loads of 1999 and 4891 kilograms are applied? So the success probability is calculated as the exponential of the regression equation of 1 plus the exponential of the regression equation. So the construction of the logit model, these probabilities are automatically guaranteed to lie between 0 and 1. Note here, you've got quite a big deviation between the values on the previous slide. So in the first case, the success probability is estimated at 0.9, and in the second case, the success probability is estimated to be 0.7813, so roughly 10%. So not only are these more sensible probability estimates, I think what you see here is the region where the previous linear probability model breaks down quite significantly. So a 90% success rate, very different to a 100% success rate, and a 10% success rate, very different to a 0% success rate. Okay, so even if we rounded the answers on the previous slide for the linear probability model, there's a clear indication here that you've got inaccuracies when either the estimated probabilities are very high or very low when you're looking at the linear probability model, and the logit model gives you more sensible estimates of these extreme probabilities.